Welcome to The Explainer. Today, we're tackling one of the wildest, most mind-bending mysteries in the entire universe. Usually, when we look up at the night sky, our eyes are instantly drawn to the shiny stuff, right? The stars, the sprawling galaxies, those glowing nebulas. But today, based on our source text, we're flipping the script. We are shifting our perspective and looking directly into the dark. We're diving deep into the massive, uncharted voids of space and the pending theories about where they actually came from. Okay, let's dive right into this. The big scientific problem we're looking at today is beautifully simple to ask, but honestly, it kind of breaks your brain to think about. What exactly lies within the uncharted voids of space? For decades, astronomers mapped the universe by tracking where all the matter is. But recently, the scientific community realized we've been missing a huge piece of the puzzle by ignoring where the matter isn't. These giant pockets of absolute nothingness, they aren't just empty background space. They're actually dynamic, active players in the physics of the cosmos. To wrap our heads around this, here's our roadmap for today. First, defining the voids. Second, the scale of emptiness. Third, analyzing the missing data. Fourth, exploring pending origins. Fifth, comparing theoretical models. And finally, the future of cosmology. Kicking things off with Section 1, Defining the Voids. Before we get into the wild theories, let's make sure we're totally grounded in the basics. Based strictly on the text, a cosmic void is a vast, underdense region of space situated between galaxy filaments. But here's the catch. Void doesn't mean a perfect, absolute vacuum with zero matter. It just refers to an area containing significantly fewer galaxies than the cosmic average. Think of the universe like a gigantic cosmic sponge. The solid structural part of the sponge is the dense web of clustered galaxies, and those huge holes in the sponge, those mostly empty spaces, those are cosmic voids. Moving right along to Section 2, the scale of emptiness. 330 million light-years across. Just let that sink in for a second. This incredibly stark, massive number represents the distance across just one specific void derived from the pending data in our source, the Boots void. To put that into perspective, our entire Milky Way galaxy is only about 100,000 light-years across. You could literally fit thousands of our galaxies inside this single pocket of nothingness. If our galaxy was plopped dead center in this void, we wouldn't have even known other galaxies existed until deep space telescopes came along in the 1960s. The profound isolation is almost impossible for the human brain to truly process. That is the sheer scale of the emptiness we're dealing with. Which brings us to Section 3, analyzing the missing data. Now, in science, missing data is basically a giant puzzle waiting to be solved. When you break down the overall composition of our universe, think about that tiny 5% slice. That is normal matter. That's literally everything we can see, touch, and interact with. The stars, the planets, you, me, all of it. The rest, 27% is dark matter, and a whopping 68% is dark energy. And here's the kicker. These voids are not just empty. They're the primary turf for that massive 68% chunk of dark energy. Because there's almost no normal matter there to pull things together with gravity, the voids are actively pushing the universe apart. This missing data in these empty spaces is literally what's driving the expansion of the cosmos. Let's jump to Section 4, exploring pending origins. So how did these giant expanding bubbles of nothingness even get there? First, let's clarify what an origin theory means in this specific context. The text defines it as a scientific model detailing the initial conditions and subsequent evolutionary processes that result in the observed large-scale structure of the universe. So we aren't just asking, hey, where did a void come from? We're asking, what were the exact, precise conditions at the literal dawn of time that allowed these specific, gigantic, empty regions to form instead of just clumping up with matter? If we trace this chronological history back, it all starts 13.8 billion years ago with tiny microscopic quantum fluctuations. By 380,000 years in, we see these fluctuations permanently stamped onto the cosmic microwave background as tiny differences in temperature and density. Fast forward to a billion years ago, and gravity is working overtime, pulling the denser matter together to form stars and galaxies. But as a direct consequence of all that matter clumping together, the less dense areas are completely emptied out. Over billions of years, they are essentially vacuumed clean by the gravitational pull of those forming galaxies, leaving us with the mature, massive cosmic voids we observe today. Next up, Section 5, comparing theoretical models. Exactly how these voids formed is actually the subject of a pretty fierce scientific debate. Impartially speaking, we're looking at two main competing ideas from our source. First, we have the lambda CDN model, which is the standard model of cosmology. It basically argues that the voids are just the natural result of standard expansion fueled by dark energy acting on the early universe. Second, we have modified gravity models. These theories argue that our standard, everyday understanding of gravity might actually be incomplete, suggesting that totally different, alternative laws of gravity kick in specifically inside these massive, extremely low-density regions. Let's break down the data supporting these models into a few key takeaways. For the standard lambda CDM model, its biggest win is that it perfectly matches the temperature and density distributions we see in the cosmic microwave background. It lines up beautifully with what we know about the early universe. However, modified gravity models are gaining serious traction because they address something called the void phenomenon. This is the very real observation that some of these voids are actually way emptier and much larger than standard mathematical models predict they should be. The text makes it absolutely clear that both models are currently pending. They both desperately need deep space data from upcoming next-generation dark energy surveys to finally settle the debate. Finally, let's head into Section 6, the future of cosmology. So, where does the scientific community go from here? The crucial point is captured perfectly in this quote pulled directly from our source material. To understand the architecture of the cosmos, we must look not only to the bricks, but to the empty spaces that define the shape of the building. I just love that. The voids aren't just gaps in our knowledge, they're the literal structural foundation of the universe's ongoing expansion. If we're only studying the galaxies, we are only seeing a tiny fraction of the physical reality of space. Which leaves us with a pretty wild final thought about our place in the universe. If these seemingly empty spaces dictate the structural integrity and the ultimate fate of the expanding universe, what else is hiding in the dark? Are these voids truly just an absence of matter, or are they holding the keys to a completely new understanding of physics? The math of the universe is still being drawn, and right now, the most exciting discoveries are waiting out there in the uncharted regions. Thanks so much for joining me for this explainer, and remember, keep looking up and into the dark.